Today on Xeno I'll be opening up another Night Owl Optics Night Vision Monocular. Now, there really isn't anything wrong with this unit, aside from the fact it looks to have an intermittent power switch, and the outside is dirty as all heck. So I want to give that a good clean, make it look as good as new, if possible. Now, I had a night vision unit before. It's one that I did a video on where I had to repair the insulation on the multiplier on the inside. Sadly, that one took a tumble and the image intensifier tube lost its vacuum. So here I am with another one because it's kind of useful. The important thing about this video is I want to go over how the insides work and some of the tests you can do to determine what's wrong with your night vision unit. The last video that I did had a lot of good questions on it and a lot of good insight, so I'm going to go through and share that a little bit more thoroughly in this video. Before I open up the unit, there are some bits of information and some tests that I want to share with you which will help you non-invasively diagnose problems with your own night vision unit. Let's take a look at what we have here. So like most night vision units, there will be two buttons. One button is for the IR illuminator on the front. The other one is for the image intensifier tube on the inside. The IR illuminator is pretty easy to test. Just press button and receive dim red photons out of the front. The image intensifier tube is a little bit more tricky. Under normal operation, when you're holding the button, what's going on the inside of the unit is there's an oscillator circuit that is switching a transformer. Now, sometimes you can hear that transformer as an audible tone, so let's see if we can hear that. I personally can't. If you hear any crackling or popping or snapping on the inside, and you see any kind of flashing or sparking, it usually indicates a problem with the insulation around the high voltage multiplier. I'll talk a little bit more on that later on in this video, as well as I talk a lot about that on my previous video. When it's working normally, of course, you should see a green image from the other side. So as I said, this one works for the most part. There are a few tests that you can do by means of the battery compartment. So let's go over those real quick. To help with this, I made my own little adapter. So what this is it's a speaker terminal set, and I have a little piece of plastic with some copper tape adhered to each side, and each one of these terminals are soldered to one of the sides of the copper. So what this allows me to do is I can slide this in between the batteries and I can connect my multimeter up. No problem. Don't need four hands. Let's go ahead and do that. Just like that. Go ahead and open these up and get the multimeter. Alright, so what I'm going to do now is I'm going to test the voltage going through the circuit. How I'm going to do that is I'm going to put this on volts. Now, the meter is a very low impedance, so that means that it's not going to bring the voltage down or let a lot of current go through. So, in the case of this unit, because we have an oscillator circuit, it's connected to a transformer, that's going to be fairly open until those transistors are switching. Once they try to switch, they're going to try to consume power, and it's going to show up here as a pretty high voltage. It has to do with the resistance in the circuit. Of course, the switching circuit, a little bit more complicated than that. And then for the illuminator on the front of the unit, we're going to get a voltage drop regardless because it's an LED, it's a diode. So let's go ahead and test those switches out. So, image intensifier tube, we should expect to see near full battery voltage. 2.4 volts about. So, yeah, batteries aren't great, but that's definitely what we get. Now, I'm going to go ahead and test the illuminator in the front, and because it's an LED, we're going to get a voltage drop. So it's going to be a lower number, regardless. 1.7. Yep, it's all good by me. We can also test the current going through the unit. I'm going to put my meter in amps DC, and I'm going to switch that over to the current setting on the meter. Oh, let's go ahead and check that out. Intensifier tube. Yeah, about 10 milliamps. That's pretty efficient. And the LED is about 80 milliamps. Now, the LED will probably draw more current if the batteries were a little fresher, but yeah, that's what you should be seeing, roughly. So, there's some numbers for you to work off of if you have problems on your own. Now, what if you don't have a multimeter? Well, what are you going to do? Well, of course, testing the Illuminator on the front, pretty easy. But, you need to test the image intensifier tube. You can use an LED like this. Not even kidding. Let's go ahead and put that in. Now we're going to test the intensifier tube. Look at that. Lights up. Now this only indicates that the switch is functional and that there is a current going through the circuit when the switch is pressed. Not indicative of a fully working circuit on the inside, but at least you know the switch is good. It won't work for the image intensifier. Sorry, it won't work for the LED illuminator because that has a voltage drop of its own. So regardless of how much you try, there's just not enough voltage going to this LED in order to light it up. Once again, doesn't matter though. Alright, well, I guess I'm going to have to set up some tools and we're going to have to take this apart. Let's start by removing the objective and eyepiece lenses. Most units are built like this. You can just take and spin them right off. That's the main one, the lens cover. Ooh, that's very pretty. That's a lovely coating. That'll give you the inside. There's the Porta cathode. We'll remove this. That's the little phosphor screen on the inside. Let's see what we have. Looks like we have 4 flathead screws in the front of the unit. Let's see if there's any screws in the battery compartment. Doesn't appear to be. The screws on this side, so looks far easier than the other one to take apart. Let's see, we need a flathead. Yeah. Well, there we go. Alright, from here, let's try to open it this way. Doesn't want to give up over here. Let's go ahead and get some pry tools. That ain't going right. What am I missing? Looks like I might need to undo this ring right here. Tool. And try and undo that. One moment. And back to our regularly scheduled teardown process. Yes, this ring right here does need to be removed. And the reason for that is because it clamps down in each side of the case on that plastic riser on the inside. So now, we can pull this apart just like that, and you'll see what I mean. There's a riser right here, and the ring just goes around it like that and holds it together. So remove that. What do we have here on the inside? We have this board right here, and it has 2 switches on it. A resistor for dropping some of the voltage going down to the LED for the illuminator, and oddly enough what looks to be a potentiometer or capacitor that can be adjusted for some reason. Not sure why that's in there. We have the battery bank, and we have the image intensifier assembly on the inside. We'll go ahead and open that up in a little bit. For now, I actually want to pull out the electronics so that way I have just a case. So I'm going to take some pictures of all the wiring, desolder it, and then start cleaning the outside of the case. And while that dries, I'm going to go ahead and open up this. We'll talk about what's on the inside. And now for the meat and potatoes of this video, take apart the Porta multiplier and see what's inside. This part seems pretty loose. It looks to be a pair of spacers in there. Keep those together. Not sure how that comes off. Let's take the 2 screws out from the other side, see what we can gain access to. Alright. It looks like we have on the inside a little rubber spacer, probably to dampen shock. A couple of other little spacers on the inside. There's quite a lot of them. 4, 5 spacers. Oh, I don't know if we'll be able to pull the tube out of that. So it looks like we have here on the outside the Cockroft Bolton multiplier, which is comprised of diodes and capacitors. So that's all insulated underneath that silicone. I think it's silicone. Is it hard or is it squishy? Oh yeah, that's pretty squishy. So it's a silicone of some sort. That's a high voltage insulation. We have this white wire that comes off of the multiplier, and that goes up to the accelerating anode on the inside. I can't see it from this end, but we should be able to see it from the Porta multiplier side. Yep. Okay, so you'll notice that right in this center here, there's a little hole. It looks to have a little mesh on it, but that's not too important. But that's where the high voltage goes. So that metal piece right there is charged with a high potential, and that comes from this wire, the multiplier. I think it's like 6,000 volts about. And then we have the phosphor screen. So green phosphor screen, just like you see in like a CRT tube. It's a monocolor. Let's see if we can pull this out. Oh yeah, yeah, it is pretty loose. Okay, that's good. Oh yeah, that gives us a better view, and I can clean the photocathode. That looks pretty dirty. On the inside, we have the ground plane. So this connects to the negative side of the multiplier on the inside, and that couples through the outside with a conductive lead paint or metal paint on the outside. So, yeah. So this is basically at the ground state, and what happens is when photons hit this, electrons shoot off the other side, and those electrons are drawn towards the positive potential because the electrons are negative. Let me draw out a quick diagram to show you how that works. I'll put that off to the side for the time being. Okay, here we go. Let's quickly draw out how the entire system works. I'm going to start with a positive meniscus lens, just like our front objective lens. I'm going to represent that as a simple biconvex lens. So just like this, just like you would have on your eye or a simple camera. And then I'm going to draw the photocathode. Okay, so how this works optically, let's say you have 2 points of color, 2 points of light being emitted. Going to be one of them right here. And we'll pick green for the other. So those are 2 points of light. And what happens is as the light goes in and through that lens, the image is going to get flipped. So let's draw those photons out real quick. This happens because of the refraction of the materials. Draw the same for the red. So the image that hits the photocathode, of course, upside down. Now the only thing that really matters with the photocathode is intensity. So we get a monochromatic emission, and the emission is electrons. So wherever a photon strikes the photocathode, you have an electron that's produced and freely able to move. So let's draw those electrons here and here, and those have just been kicked off the coating on the inside. Interesting to note, the coating on the inside does not have to be optically transparent. Let's go ahead and take a look at that. So the coating of the photocathode is actually somewhat fairly electrically conductive, and when the light hits it, it knocks an electron off that coating. It has different sputtered layers of metal on there. And there are different coatings depending on the application. As I said, they don't have to be optically transparent. So for example, we have a Vidicon tube here with one type of photocathode coating and another one. Let's get a better focus on those. So, for example, these coatings are not optically transparent and yet perform the same function. Another coating that is a photocathode is on a photomultiplier tube. This is actually quite optically transparent in contrast. And if you want to know more about how these guys work, look up what a photomultiplier tube does. They have really cool devices. Moving forward, well, let's take a look at what we have here. Well, we have the photocathode in the front. We have this high voltage wire, and that's going to put a positive potential on an accelerating anode on the inside, or an electrostatic lens, an Einsel lens. We can see the same similar setup in the little CRT indicators. So let's show you one of those. So just like in the image intensifier tube, we have a piece of metal here with an aperture, and what that does is when there's a high voltage potential that's positive, the electrons that are produced by the electron gun get pulled towards the positive, and then they fly through that hole and hit the phosphors. The only difference between how this works in this case and the photomultiplier tube is that our source of electrons are not from an electron gun, but instead produced by the photocathode. Let's draw the accelerating anode inside of the image intensifier tube. We'll draw it like this. So, a little hole. We got the material like that. And then we have the phosphor screen. So let me draw that. So there is our phosphor screen right there. Represent that by green because that's what the phosphor color is. So here's that part inside with the hole, the accelerating anode. So that part right there. And then the phosphor screen is the green line. Now, what's interesting is that the image is reversed here, but when you look through a night vision tube, you don't see a reversed image. Well, that's because the accelerating anode acts like a lens. It's an electrostatic lens. So let me draw what happens. The intensity of the electrons, or the amount of electrons that are produced on the photocathode, is determined by the intensity of the photons that hit the photocathode. So the more photons hitting the photocathode, the more electrons are produced. And those electrons are accelerated towards the positive because of their electrical charge, negative, positive, so they attract. So then these charges, these electrons, get pulled in through here, just like this, and kind of come out the other side, like this. It's a very simplistic drawing, but you know, it gets the point across. So the image that you see in a night vision intensifier, the night vision monocular, actually gets flipped twice. And then with the eyepiece, let's see, we'll represent that real quick too. Here is that lens represented by another positive meniscus lens of poor quality. And then those photons, once again, black and white, just go through here and out to your eyeballs like that. Fun stuff. There, we'll make it even more lively. There's you. There's you holding the device. Pretty simple. At this point in the video, I'm at a little bit of an impasse because I can't easily access the board inside of my night vision unit, and I don't want to risk breaking it. I already broke one. I don't need to repeat that. However, they're usually single transistor oscillators. I think they're Colpitts oscillators, but I'm not sure. So my best recommendation is if you're not getting any high voltage out of your transformer, and I'll show you how to test for that later on in the video, my recommendation is to find the transistor and read the part number on it. If you can find a replacement or an equivalent and get a new one in, you should be good. That's about the best I can say on it. I'll get into other options later on in the video. But before I do, let's take a look at how the night vision unit looks now. I didn't think this was going to involve wet sanding, but it did. Ta-da! You can rate my refurbishment job on a scale of 1 to 10. I would personally give this an 8.5. It could have been better, but it looks pretty okay. Yeah, the black I think is a much better color for a night vision unit. Alright, now let's get into the high voltage options. Alright everybody, get out your notebooks because I'm about to give you a little bit of a crash course on high voltage and how you can achieve getting the correct power to your image intensifier tube. So from what I've seen, a lot of the Generation 1 image intensifier tubes that you'll commonly run across with normally run at about 4 to 8 kilovolts comfortably. So let's go ahead and start off our diagram with that. We're going to draw a little ground over there. I'm going to draw the positive over here. That goes to the accelerating anode. This is ground. And then let's label that 426 kV. And that goes to the image intensifier tube. So inside of the night vision units, there's something called a Cockroft Bolton voltage multiplier. Let's go ahead and show you what that looks like. Here's a much larger one that I have made, and it's composed of two things, and it's the same two things that are inside of the night vision unit, except a different form factor. I think they use SMD. These are through-hole components, but only two things, diodes and capacitors. So that's represented on a lot of diagrams. And there's two ways to build them. You can build them positive and negative, and that's important. So let me show you what positive looks like. You want the diodes going in the correct way to give you the output. So in order to get a positive output, we have to draw all the diodes, place all the diodes in the way that they would give us that positive output. So anode side going towards the output. So let's go ahead and do that. We're going to draw one diode like this. Right, and we're going to start zigzagging them back and forth. Let's go ahead and draw 2 stages. We're gonna put the cathode towards the output because the power is gonna flow from the positive this way. We're gonna draw the cathodes in just like this, and then we can do the little arrows. Alright, so now we got some diodes. Now let's draw in the capacitors. We're going to have one cap between these two, so let's go ahead and do like that, out like this, and each one of these represents a capacitor. So capacitor here, capacitor here, capacitor here, and one final one right over there. The base of the multiplier would end up going to the ground here. So let's go ahead and draw that in. We're going to have to go around, I think, to make it easier on us. Right there. And then the AC from the transformer goes into the capacitor here and here. And this is our voltage multiplier circuit. The voltage output depends on 2 things. First of all, the voltage input and the amount of stages that you have to a point. I say that to a point because there are diminishing returns, but for example, here's a voltage multiplier built in the same way with many more stages. The only difference between this multiplier and the one that's in the night vision unit is geometry. Basically, that one is just wrapped around the outside of the image intensifier tube. Now, what do you need to drive a voltage multiplier? Well, you need an AC input. It can't be DC. So let's go ahead and mark that down right here by a squiggle like this, indicating that our input to that must be AC. Well, we get that from a transformer. So let's go ahead and draw the high voltage side and a low voltage side because it's a step-up circuit. Now I'm going to draw the high side of the transformer in orange, and I'm going to draw the low side of the transformer in purple. So thicker coils, less of them, more coils, thinner coils. Go ahead and connect that up because it's AC. Well, I can use green again. So right there, that's the transformer. And the transformer must be pulsed, or it must get a signal, but I'll get to that a little bit later on. So say you just want an out-of-the-box solution that's pretty easy. Well, there's a couple of things that you can try and use, and they have their advantages and disadvantages. So the closest thing I can think of that you could easily get your hands on is the Porta flash charging circuit from a camera, whether it's disposable or not. The downside is that the output that goes to the Porta flash is in DC, so you have to find the output of the transformer and bypass the diode, so that way you get AC. And there's a way to tell whether you're getting AC or DC. It's pretty easy. Let me show you that real quick while we're here. And that is the little neon light. I'm going to hold it like this because I don't want to get shocked. Let's go ahead, connect it up. Alright, if you look at the neon light closely, you should see that only one side is lighting up. And that would be the right side. If it's AC, both of them will appear to light up, but in reality, the output is just jumping back and forth between those terminals. If you see only one terminal lit, it's not suitable to drive the voltage multiplier. Keep that in mind. More options include things like the CCFL inverters from laptops and other things. So these will give you an AC output, although it's best to tap directly into the areas, the leads coming out the transformer, bypassing these capacitors here. Some of them work better than others. Quick note actually. The upside to using this is they're actually pretty efficient little step-up circuits. They don't require a lot of current. Sad thing is they might require more stages because the voltage is not quite that high. The CCFL inverters will give you anywhere from like 2000 to 3000 volts, so all you need to do is double or triple the voltage. Other options include larger CCFL inverters. So for example, here's another one. This one again will give you about 2000 to 3000 volts AC out. You have to bypass the capacitor and it should work just fine. I will make note that if you're experimenting with your own power supplies and powering your image intensifier tube, it might be wise to throw in a resistor, say half a megohm to 1 megohm, just to prevent too much current from going into your image intensifier. Let me draw that in. Draw the resistor in orange because resistors get hot. Now we'll say 0.5 to 1 meg ohm. Boom, done. Alright, now there's a downside of using things like this, and that is that they require more voltage to operate. They will not operate at 3 volts and usually start operating at about 6 volts-ish, and that means that you're going to need to, say, for example, in mine, since I'm using the AA's that are alkaline, giving me 3 volts, because there's 2 of them, I will need to use 2 lithium-ion batteries, and therefore need to change out the resistor inside of the unit. That's like 10 ohms, I think, for something of a higher value, anywhere from say 50 to 70 ohms, and that should give you the right 100 milliamp current going through your LED indicator. I have a lot of things going on through my mind, and I'm just getting warmed up. All right. Another option is, say you have your own transformer and you want to power it. Well, that can get tricky. You can go about it 2 ways. You can either use a PWM chip, or you can use an oscillator. Suitable transformers, I would suggest, would be the ones that come from the CCFL inverters too. There's a lot of these you can find, and they're wonderful to use for your own high voltage projects. But there are options. So we're going to keep this in mind that this is going to be, say, a general CCFL transformer. You can drive this by a couple of means. One of them is a PWM chip or timer chip, like this 555 circuit right here. This is a pre-made one, but you can look at, say, Eric's flyback driver and drive your transformer that way. On these boards, there's a couple of settings. There's these jumpers, and what these jumpers do is they add capacitance by putting these capacitors in parallel. So the more jumpers you have, the more capacitors you have, the higher capacitance and the slower the frequency of the output of your 555 circuit. There's also a potentiometer right here on the side, and I believe that that's for fine-tuning the frequency. It could be for the duty cycle as well. I don't remember. This chip is dead. I can't test it. Zooming out again. So if you want to use a 555 timer, you're going to drive it with an N-channel MOSFET. So let's go ahead and draw that in. So here's our MOSFET. Right here, the gate is usually the center pin and is output. This side of the transformer's low side is going to be connected to positive. So like that. And then we have 3 pins on here. We have VCC, positive voltage in. We have ground, and we have signal out. So let's go ahead and draw those. Say this is plus in, so that's connected also to the same positive going to the transformer. And then we have the signal out. Let's draw signal out as green, and we're going to run signal out right to the gate of the MOSFET. So this will be signal out. That'll go to the gate of our MOSFET. We can throw in a little resistor, say 5K in there, but with lower voltages, it's not exactly needed. You can also throw a pull-down resistor in between source and gate if you want. Maybe say 50K, something like that, but it cannot be a lower value than this. The lower value? Yeah, it needs to be a higher value. So for example, this is 5K, make that 50K. That way you can get a positive signal into your MOSFET and turn it on. And then of course, ground. So we have a negative that goes into the board. And then that negative would also join with the MOSFET. So that would be how you use one of these little drivers like that to drive a MOSFET. It's pretty easy. Let's say you don't have a little PWM timer. Options, I guess. Here we go. Let's say you need to have an oscillator, something like that. That's where it gets tricky. That's a whole topic in of itself, but I have a little bit of knowledge in some oscillators. To represent oscillators, we're going to have a little astable LED multivibrator flashing to keep us company. Alright, so oscillators. The reason why we need an oscillator is because we cannot power a transformer with a DC voltage, DC current, because once you establish a magnetic field inside of a transformer and it's not moving, there's going to be no activity on the secondary side. So we need to have a voltage that fluctuates either by pulsing or by flipping and inverting the voltage. So there's two ways we can do it: pulsed DC or AC. The 555 timer is pulsed DC, and you can set your own frequency. But say we don't have a 555 timer and we want to make an analog circuit. The one thing that I have the most practice with is the zero voltage switching circuit. I've started to use a slightly different version. I'll go ahead and throw up a schematic so you can see the general layout, and you can mess around with the values of your own components. If you have any kind of questions as far as the components you should use, I would say watch the ZVS video that I posted up. It's not 3 hours for nothing. These get complicated. The upside to these is that they give us an AC output. So we can't see it inside as far as what side is lit up and what side is not, so you're just going to have to take my word for it. The upside to the CVS circuits is that we can tailor make them to our input voltage. So for example, this one will work happily on a single lithium ion, and we'll do it no problem. And we can connect this up directly to the voltage multiplier without a problem. Done. Another circuit you might want to look at is the Slayer exciter. For example, here's a little Slayer exciter that I built, and I just used the coil from a little stepper motor, and then a larger coil as my primary. And this also works and gives us an output, although the current that we get from this is very low. But it does work. The voltage could be a little higher too. But you can see that light bulb light up just a little bit, but it's not very much. You can use a MOSFET for a similar circuit as a Slayer exciter. So here's one that I've shown you before. And I made a couple of kind of tweaks to it so that way it runs better. This is the original circuit right here that I built. It uses a single transistor, a single MOSFET. And we can get 2 neons to light up with a single lithium ion battery. That's not bad, but it's not great. I'm going to go over a little bit of how I made this. All the secondary is a relay coil, and I wound another coil around it, which gives me the primary coil. I don't want to go through the circuit and explain it all too much. I'll throw up a diagram of what I did to make the circuit, but it's pretty simple. You know what, heck, I can draw the diagram here in a little bit. On the upside, I have managed to make it much more efficient by putting more smaller turns on here. I can't believe how efficient it got. So this one with the thicker wire will light up 2 neons with this battery. I'm gonna blow your mind because that one will light up all of these neons with this battery. That's nuts. I can't believe how well that works. That's gotta be like 400 volts. That should power a doubler, a multiplier, no problem. We're gonna find that out later. A MOSFET might go bang. Here's a fully functional ZVS that I built, and it has a little cold cathode inverter transformer on it, as well as a little voltage multiplier circuit ready to go. When you get one of these running, you should get a reasonable output. This one isn't up to full voltage, but gives us good indication of what it should look like. So you can make your own, no problem. It's not that difficult to get high voltage. Practice at it. Let's take this multiplier off and see if my little, actually, you know what? Beforehand, I'm going to draw that circuit. Alright, so once again, starting with the MOSFET. Let's draw the MOSFET. Let's find the black marker. We're going to draw the MOSFET like this. Once again, 3 leads, source, gate, and drain. And we're going to have a negative here. And the negative is going to get connected to the source just like that. We have our positive. Once again, the positive goes directly to the transformer primary like this. And then we have this. So what I've done is I've taken one side of the secondary, just like you would do it in a Slayer exciter, and I have connected it to the gate through a resistor. Oh, here's that resistor, and that is 10K. I also have between, in parallel with the transformer primary, a 1 microfarad capacitor. That's AC. So I'm using a poly plastic cap. That should be like that. I draw it green because it's AC. So when building your own oscillating circuits like a ZVS, you always want to use these little poly caps or ceramic caps. Don't use tantalum or electrolytic because the voltage is going to be switching back and forth. It's an oscillating circuit. That's what it does. Yeah. Let's connect this up to a voltage multiplier. See if it goes bang or if we get output. I have never run a little voltage multiplier like that off a Slayer exciter. And from what I know, the Slayer exciters don't like being loaded all too much. Come on, warm up. Alright, here we go. Take that off. Alright, here's our little voltage multiplier. It's like that. Oh, I forgot something. That's not right. What am I doing? Alright, no, sorry. I made a mistake. That gets directly connected to the gate. The positive goes to the 10K. I love this program. It's easy to fix mistakes. Alright, where were we? Yes. Sciencing. Yeah, I want to have it this way. Just because I want to have the, or do I? No. No, I want it on this cap because I think that is going to be preferential. I don't want to pull down the signal going to the MOSFET gate all too much. I've never done this. We're experimenting together. This is why we're a community. Okay. Ooh. Here goes nothing. Let's try this. Wow. I can't believe how well that works. Look at that. That's using a 24-volt relay for my primary. Or sorry, for my secondary. That's bonkers. That's absolutely bonkers. Yeah, so here's the relay that I used for that. A little, I think these are 24-volt relay. Yep, 24 volts DC. I usually have tons of them. This is not the only bin of them either. This is not all of them. If you need one of these, I guess let me know. Tons of them. But yeah, so what I did is, yeah, I just wrapped the another wire around the relay coil. I didn't even put anything in there for a saturable material. That's nuts. I wonder how big we can get at. Let's try that distance. Say that's about 8 millimeters. So that would give us 8 kilovolts. She won't shoot yet at that. Try more power. Oh. That's nuts. That is super nuts. Alright, well, on that note, I guess that's all the advice I have for high voltage options. I'd say it's about time to wrap up the video, so let's go ahead and do that. I want to give you some final thoughts on this little circuit. Seems to be a very good circuit, and there's a likelihood that you could just connect this right up to the multiplier inside of your night vision unit and get it working at 3 volts, no problem. There's upsides and downsides. It's easy to make, and the parts are easy to locate. The downside is it's kind of fickle. If you have a relay coil of a different size and different voltage, or just physically larger or smaller, you may need to change the value of the capacitor, usually bigger for bigger coils, smaller for smaller coils. And you may have to fine-tune the resistance inside of your circuit. So what I have here is a 20K potentiometer instead of a fixed 10K one that goes between the MOSFET gate and one of the outputs of the original relay coil. Let's see, what else is there to note? If yours does not oscillate, I would recommend you flip the wires that you put on. So just flip them around on the primary. Sometimes if you wrap it backwards, it doesn't work, and it works better flipped one way than the other. And that's common to most Slayer exciter circuits. But yeah, you can get these things to run pretty good. So here's one that takes less current, lights up all those neons pretty easily. But if you think that's impressive, let me show you something that's really impressive. I cannot believe this works. Okay. So check that out. I actually added a little bit more capacitance on this circuit. Put a little bit of cooling on the MOSFET because it needs it. But I can get this helium neon laser to run, not very much, but I can get it to run up a 3-volt CR2 battery. That's crazy. About 1 amp, 3 volts. A little less than 3 volts. Battery is up to about 2.8 volts, but still, that's nuts. Alright, let me show you that. Is that the right way? Maybe that's the right way. Alright, here we go. Oh, that's the right way. Look at that. That's incredible. Look at that. Not much. But it does work. And that's a nice segue into why I want this night vision unit. So, the reason why I want this night vision unit is because I don't have anything that sees the 355 nanometer beam from my OBIS. So, the night vision is the one thing that I do have that might be able to see that beam. So, what I'm going to do is I'm going to plug this laser in. I'm going to fire up the night vision unit, and we're going to see if we can see that beam that way. Alright, I have my 355 nanometer laser up and running right now. Let's go ahead and stick something thrust in the beam path. Yep, there it is. But we can't see any output from the laser. I can't see it with my camera. The human eyeballs can pick up 355 nanometers. But let's see if an image intensifier can. Here we go. And I still have the pinhole cover on because I don't want to damage that. Wow, look at that right away. That is cool. So yeah, you can absolutely see one of these ultraviolet lasers with an image intensifier tube. That's cool. That's something you don't see every day. Neat. Still green though. I want to see that firsthand, but I can't. Alright, well that's interesting, but it's not really exciting, so yeah, let's take this night vision unit outside and see how it really works. Alright, here I am in the dark and cold of winter's night, so it's going to be a fast review. Anyway, this is with out night vision. Let's try the night vision out now. Here we go. Oh, yeah. Not too bad at all. Looks good. Looks nice and bright. Pretty clear. I'm actually a decent fan of the night owl optic stuff. They seem to work very well. Anyway, it's pretty cold out, so I'm going to go inside and make myself something warm to drink and enjoy that. I hope you enjoyed this video, and as always, stay tuned for more.